Hey, Matt Mathersum here with Math Madness. Thank you so much for joining us and being a part of the program today. You know how we feel about it. Thank you for being here. We really do truly appreciate it. You've heard me speak about Paws Saving Paws, this wonderful organization out of San Antonio doing phenomenal work with rescue dogs, fostering, adoption, transportation. These guys, they have big hearts, but they need big help. And if you are in a position to offer that big help, please reach out to Paws Saving Paws. You can even head over to my TikTok channel at That's My Dog to have more information provided for you there as well. All right. Today we will be integrating work. Just when you thought work could get any more integrating or irritating, depending on your perspective, well, let's just go ahead and get to it. We're going to utilize a little bit of physics to demonstrate this illustration. Well, you know what I'm trying to say. Let's go ahead and get to it here. We've got work is going to be equal to force times distance. This is a very simplistic formula for us to start out with. And as you know with me, it'll probably get a little bit more challenging, but it's nothing you can't handle. So let's just go ahead and get to work equals force times distance. Well, let's say that we have a box here. It's sitting on the ground. We've got a wooden box here, and I'm pushing it with F amounts of force. And in this case, we will be dealing with Newton forces, since that's how forces are registered, if you will. Well, this is going to be a constant force. So at some point in our life, I will have this box positioned over here. Again, at this point, I'll have forces, Newton forces going again here. They will be constant as well. Well, we've got a distance here, don't we? We do. We've got a distance here from here. All right. Well, what is this actually telling us? Work equals force times distance. Well, my artistic work notwithstanding, it just simply means that if I know this distance in meters, which is how we calculate distance, and if I know my force in newtons, then that will provide us the work in joules, won't it? It most definitely will. But life doesn't always offer this opportunity, does it, to just push something straight forward? No, sirree, it does not. Let's look at this from a different angle, and that is a pun intended. Okay, again, we've got this same box, my artistic work notwithstanding, but this time we're doing this from a different angle completely. We're doing it from this angle. That did not turn out right at all. Let me just try that again so we get a better perspective here. Okay. We've got our force here. Okay. Well, how do we calculate this? Because this is not the same as going on over here, right? We've got something that's being pushed at a straight on direction. Now here we've got an angle, don't we? And we've got angle theta. This is actually what this is. This is our angle theta. All right. Well, again, this is going to be force in newtons. We know that. And again, over here, this box will get to this point at some point. And again, we've got this force going on here, don't we? Okay, and I do have that in newtons as well. I don't think I wrote that down here. Let me get that. All right, we've got force newtons here. And again, this is angle theta. All right. Well, the problem here is we can't use force times distance in this particular instance, can we? Because here it's going straight on, right? I'm pushing it straight on the x-axis. But here I'm pushing it down. Yes, it is moving forward, but I've got a lot of force coming down at this angle. How do we rectify that? Because I'm only interested in the force and the direction of the motion that we're pushing. In this instance, it's along the x-axis. Well, we modify this simplistic formula, don't we? Now what's going to be work? Well, work is going to be equivalent now to force times cosine theta times distance. You know, I ran out of room here. Let me just write it over here. Work is going to be equal to force times cosine theta times distance. This is our modified formula, all right? Well, what is cosine theta actually doing for us in this instance? I mean, it's being multiplied by this magnitude. How does this help us? Well, what this is going to do is it's going to flatten this diagonal force for us, right? When we multiply this by the magnitude, this will isolate the direction that we want to find the force for. In this particular case, it's along the x-axis. Let's just draw the right triangle here real quick to demonstrate exactly what we're talking about here. And that'll give us a good picture here. Here's my right triangle. Again, my artistic work notwithstanding. So we know that this is the hypotenuse right here. We're all aware of that, right? No news there. And this is our cosine theta. We're all aware of that. And this is our sine. Well, let's go ahead and deal with some substitutions here. Let's make our hypothesis. Let's make our hypotenuse our total force in this particular case, and that will be represented as such. Our cosine theta, that's going to represent the x force along our x-axis. That's what we're trying to solve for in this particular case. And our sine, well, that's just going to be the force of the perpendicular, and you'll see sideways as well. That's why I've got the PS here for that. Well, what are we solving for? We're solving for the force on the cosine theta direction, right? So let's go ahead. We know what cosine theta is. We just know cosine theta is equal to adjacent over the hypotenuse, right? Well, let me plug in the correct values here. Again, we got cosine theta, and that's going to be equal to the force along the x-axis, which is what that represents. And the hypotenuse, we said, is the total force. So there's our total force. We're solving for the force along the x-axis. We want to isolate for the force along the x-axis. How do we do that? Well, the formula right here says work equals force times cosine theta. Force times cosine theta. So let's multiply force times cosine theta. We're going to isolate for the f of x over here, and it's going to give us something along the lines of this, isn't it? Cosine theta equals f over x. That's our force along the cosine theta. And multiply by our total force. I'm going to isolate the f of x by multiplying both sides by the total force, aren't I? These will cross out over here, isolating the force on the x-axis and giving us the cosine theta multiplied by what? Right, by our total force, which is F, which is what this formula stipulates. This is our total force being multiplied by the angle of the cosine theta, multiplied by the distance to give us the force on the x-axis, which is what we're trying to solve for in the first place. I just didn't want to gloss over this and just say, hey, apply cosine theta to the force and everything will be okay. You need to see this particular operation, the mechanics behind it, and why it works. And I encourage you to look at this a little bit further on your own. We are dealing with vector forces, and what this cosine theta is, it's a vector resolution in this situation, allowing us to isolate and solve for the force and the direction of motion that we are concerned with, which is along the x-axis in this particular example. All right. Well, let's do this. Well, I have it on my mind. Let's do a force distance diagram. And this is going to demonstrate exactly what we're talking about here. We've got force newtons here, and I've got my x distance in meters. And let's say our box starts here. Let's use 5 newtons as our starting force, okay? And let's say we start here with 5 newtons, and I'm going, and now I'm tired, and I'm going to drop the ball right here, in this case, the box. Well, let's say I've moved 10 meters in this particular instance, okay? What are we trying to find here? Well, we're trying to find the work in this area, aren't we? Right, work in joules with the distance of 0 to 10 meters. Well, remember, our simple work formula is just simply force times distance, isn't it? So if I know my distance and I know my force, then I can get my work. So in this particular instance, our work is equal to, well, our force is 5 newtons, and our distance is 10 meters. Well, let's see. 5 times 10 gives us 50, doesn't it? Which is 50 joules. That's how our work is measured in physics, with joules. All right. Keep in mind that this formula is good for when force is constant. Now, that's all the time we have for in this particular episode. Next episode, I'm going to show you what happens when force isn't constant and things change up. Things can get a little messy. You're not going to want to miss that. That's all the time we have for here on Math Madness. I'm your host, Matt Mathersum. I'm going to see you guys really soon.